Okay, today we will talk more about cation exchange reactions. We already covered some aspects of cation exchange, if you remember, when we talked about the inorganic components of soils. Today we'll go a little bit deeper and from different aspects of cation exchange reactions. So if we take the first reaction, Na2X plus Ca2 plus aqueous, that means it's in solution, gives you CaX and 2Na plus aqueous, again ions in solution. In a minute we will talk about what's X. Or if you have this reaction, 2NaX solid plus Ca2 plus, the same, gives you CaX2 plus 2Na plus. This is, again, the ions in solution. X is the exchange complex. That's a general term. It can be, what do we mean by an exchange complex? It's the colloid that exchangeable reactions can take place on its surface. It can be a silicate clay minerals like kaolinite, montmolonite. It can be humus colloid, any colloid in the soil that has negative charges that can adsorb exchangeable cations, and this type of reactions can take place. So we'll explain the two reactions. In the first reaction, the exchange complex, think of the exchange complex, any soil colloids that can have exchangeable cations on its surface. Okay, so in the first reaction, the exchange complex X, we call it, was described as having two negative charges. So X has two negative charges. That's why if it has two negative charges, it needed two sodium ions to neutralize these charges, Na2, two sodiums on the surface of this colloid to neutralize its negative charges. We added to this calcium ions, so the calcium is going to exchange or substitute the sodium. Of course, remember, we said the exchange reactions charge to charge. You should remember that. If you have forgotten that, go back and review what we have already discussed. Charge to charge. Sodium carries one charge, so you need one calcium that carries two charges, two positive charges, to replace two sodiums. So now on the complex surface, we will have CaX, only Ca. It replaced two sodiums, two positive charges, same charges. Plus, it released the two sodiums that were on the surface of this colloid. They are now in solution, 2Na plus aqueous. That means they are in solution. So this one has two negative charges, this X or this colloid. Whereas in the second reaction, the exchange complex X exhibited only one negative charge. It carries only one negative charge. So one negative charge, it needs only one sodium ion to neutralize that negative charge. Forget about the two. This is stoichiometric number. But this is NaX instead of Na2X. We have now NaX, one sodium on the surface to neutralize the negative charge that X has. Now, if you take two of those colloids, two is ahead of them, so that's two of the colloids that each one of them having one sodium on its surface, you need to add calcium. Okay, how is it going to replace? It has to replace two of those. So we say CaX2. It needed two of these X's because it has one negative charge. Calcium has two positive charges. So you need two of those, each one of them carrying a negative charge to neutralize the calcium charges. And of course, the 2 sodium will be released the same. 1 sodium coming from each X, so you have the 2 sodium coming into solution. There are some generalizations, some important things to notice and observe and learn about the exchange of cations in soil. So generalization about the attraction, exchange, and retention of cations by soils. Cation retention by soils can be divided into the weaker electrostatic interaction of soil particles with alkali and alkaline earth cations. So the first one, the attraction is through, remember, I have told you earlier, whenever you hear electrostatic attraction or interaction, we talk about the attraction of positive, negative. So this is a weaker type, the weaker electrostatic interaction of soil particles. And this is usually when you have the alkali, remember, alkali, sodium, potassium. We talked about this earlier also, or the alkaline earth, calcium, magnesium. So you have sodium, potassium, calcium, magnesium, all these ions, their attraction will be weak through electrostatic interaction. Then the soil's stronger chemical bonding with trivalent and transition metal cations. Some other metals, they are attracted with chemical bonding involved. So the ones with the trivalent and the one in the transition metal of the transition in the periodic table. Chemical bonding is the interaction of polyvalent cations with O2. So the chemical, when we have bonding, that means there is an interaction. Of course, the oxygens will be the oxygens on the colloids that we talked about, and OH minus ligands of aluminosilicates, hydroxide, phosphate, and retention by soil organic matter by humus. So in this case, polyvalent, that means the cations that have multivalency, like we said here, can be trivalent or more, or the transitional type metals. Okay, we first talk about the relatively weak electrostatic attraction. We said the alkali and alkaline earth cations. I have already told you they are potassium, sodium, calcium, magnesium. What is so important to know about this type of attraction? First, they are non-specific, depends mostly on the concentration ratios on the solid, which means which of the ion is higher in concentration, it will take the place of the one on the surface. That means non-specific. None of them is held in a very specific, tight way, so it will not allow another ion to exchange it or move it out of the surface of the colloid. So these are simple one, non-specific. That means each one of them can take the place of the other easily. Okay. So non-specific depends mostly on the concentration ratios on the solid versus the soil solution. We will talk about the ratios a little later. Some clay minerals prefer one ion over the other. There are some that prefer, say, certain ions, but that's still not super specific in that sense. Reactions are fast and reversible. So this type of reactions take place very fast. Fast, what do we mean? Time scale in seconds and minutes. So if one cation takes the place of another, that process happens very fast. In a matter of seconds or minutes, the whole process is finished. So it is fast and reversible. If you increase the concentration of the one that is in solution, it goes back and takes the place of the one that was replaced. So that's what it means. It's reversible, can go back and forth depending on the concentration you have in solution around the colloid. Amount of retention depends on soil CEC. How much of it, of course, because remember, CEC represent the total negative charges that are on the colloid's surfaces. And so the higher the CEC, of course, the greater the amount that will be adsorbed, largely due to aluminosilicate clays plus organic matter. What are the colloids, the X that we talked about earlier? They are aluminosilicate clays and humus, organic matter. Then we have the other type, we said the strong attraction that involves chemical bonding attraction. This includes hydrogen, aluminum, beryllium, titanium, transitional metal, and heavy metal cations. If you notice here, we put H. H has very unique and different position compared to all other monovalents. So we did not put it, say, with potassium and sodium. No, we put it just like the polyvalent cations. It belongs to the stronger ones. Hydrogen in its chemistry, totally different from the other monovalent cations that are in the solar system. The strength of attraction depends mostly on the cation's water solubility and the amount on surfaces of soil particles. So it's not non-specific easily. One can take the place of another easily. The strength of attraction depends mostly on the cation's water solubility, how easily its compounds dissolve in water, and the amount of surfaces, the amount of that cation on the surfaces of the soil particles or the soil colloids. The action time scale is rapid at first, but continues at ever slower rates for long periods. The other one we said almost instantaneous, seconds or minutes. In this particular case, no. The reaction time scale is rapid at the beginning, but then as it continues on, it goes slower and slower for long periods of time. The amount of retention depends on soil pH rather than on the charge properties of soil clays. So how much is attracted depends a lot on the pH of the system, the soil pH, instead of just the charge properties of the soil clays. Aluminosilicates are less important. So the aluminosilicates were very important to never remember. We said aluminosilicates and humus. In this case, aluminosilicates are less important, and we have iron and manganese oxides are more important. So the oxides are much more important because they depend on the pH. Their charges are pH dependent. Mechanisms of retention are complex. The mechanism, how are they attracted? Not simple, like the other one was electrostatic attraction between positive and negative. Organic matter increases the range of sorptivity. Of course, the organic matter always have very high CEC, so it increases the range of sorptivity, how much will be sorbed or adsorbed. The sum of all exchangeable cations present at a given pH and CEC varies little or not at all with cation species. So what are the cations that are there and what are the cations in solution? That's not what's important in the total sum. The sum of all exchangeable cations present at a given pH and CEC varies little or not at all with cation species. Of course, if you remember, charge for charge. So it doesn't matter what are the species, what are the different cations you have. So X, again, we call it cation exchanger or exchange complex. We called it before, it's the same. CAX, okay, so in this case, remember, CAX, so that has two charges, because calcium is neutralizing the charges on that. Calcium is divalent, plus 2 ammonium, so that we needed the 2 ammonium to take the place of calcium. Charge for charge. Calcium carries 2 positive charges. We need 2 ammonium cations. Each one of them carries 1 positive charge to replace the calcium. So now we have NH4 2 on the surface of the X, and then calcium is released into solution. 2 ammonium ions replace 1 calcium ion, to preserve the stoichiometry of the reaction. We already talked about it and we know that. Exchange reactions are also rapid. The exchange step itself is virtually instantaneous. So the actual exchange, that means one taking the place of another, virtually, that means almost instantaneous, means immediate. I mean, it takes no time, instant. Like when you say in instant, that means extremely fast. So that doesn't take really any time. The actual exchange process, the exchange step, the rate limiting step often is ion diffusion to or from the colloid surface. We'll read it all and then I will explain it more. This is particularly true under field conditions where ions have to move through tortuous pores or through relatively thick stagnant water films on soil surfaces to reach an exchange site. So remember, we said why sometimes the exchange process, not the exchange step itself, one taking the place of another fast, but for one cation to reach the position of the other one that's adsorbed, to get there, that's what takes time. The rate limiting, what makes this fast or slow, is that step. What is that step? Is the ion diffusion to or from the colloid surface. If it's the one going to the surface, that's diffusion to, or if it's leaving the colloid surface, it's diffusion from that surface. So either way, diffusion, remember, is moving from from high concentration to lower concentration, diffusion of ions. This is particularly true under field conditions. When you have in the soil, in the field, in reality, where ions have to move through tortuous pores. Tortuous pores, that means they are extremely difficult, winding, zigzag. That means the ion has to go through because they're not straight lines. They're not, you know how the pores of the soil are very complex and they are not all connected one to the other like a channel. So they are very intricate, tortuous pore paths. And the ion has to go through all that. It has to go through all these difficult paths and also through the relatively thick, stagnant water films on salt surfaces to reach an exchange site. So for it from the salt solution to go to the site of the colloid where it's going to exchange another, it has to go through the pores that are extremely difficult paths, and it has to penetrate the thick, of course, thick in terms of that ion, not thick in terms of the way we think in our sense, the sense of that ion. Because where is the water? Water surrounds soil particles as films. These films are stagnant. Stagnant, that means they're not moving. They're there. They're attracted to the surface of the colloid. And of course, this ion that's going to the surface of the colloid has to penetrate that water, which is as a film on the soil particles. After it goes through all these tortuous paths also to penetrate that stagnant, which is still not moving, water films until it reaches the surface of the colloid. So this is what takes time. After it reaches that, then the exchange step is very fast, but it has to reach that site. This is what it takes. This is the time consuming. This is the rate limiting step. Because of their reversibility, cation exchange reactions can be driven forward or reverse by manipulating the relative concentrations of reactants and products, just like any reaction. When you control what's in salt solution, you increase the concentrations in salt solution, it drives that the other way. It goes more of that, what you added, more of what the cation that got higher concentration will go to the surface of the colloids. And the less, of course, it will be the other way. So In laboratory, common techniques for driving the reactions toward completion is to use high concentrations. High, which means equal or greater than 1 molar concentration of exchanging cations, and to maintain low concentrations of products cations by leaching or repeated washing. So if you want one cation to replace another that's on the surface of the colloid, what do? The one you want it to replace the other, you increase its concentration in solution. How? You make the concentration of it at least 1 molar, 1 or more molar concentration. If we do it in the laboratory, suppose we want to exchange. Okay, remember, we will talk about it later when we talk about the procedures or the methods of measuring CEC of the soil. We'll talk about the same thing. Sorry. So, concentration and to maintain low concentrations of product cations by leaching or repeated washing, because you want that concentration to be high, and the ones that come out, you have to keep them low. They're the product, what ends up, you have to remove them or keep them low in concentration to keep the process going to the right. So let's take an example. CaX, so we have a colloid with calcium adsorbed to the surface. Of course, remember, calcium divalent, it needs 2 sodium. So we put sodium in high concentration, at least 1 molar concentration, high concentration, to push forward to the right. So the sodium will take the place of calcium. Of course, you need 2 sodiums. Each one of them is monovalent to take the place of a divalent. Plus calcium, you need to keep this calcium that came out low. If this keeps high concentration, of course it's divalent, it will push the reaction that way. So we need to keep this concentration low to form insoluble precipitates. So we can see how we can make this one low by adding, say, sodium carbonate, CaX. Here we put just the ion. If we add it in the form of sodium carbonate, it still give you 2 sodium plus, and then it will give you the carbonate ion. The carbonate ion will combine with the released calcium to form calcium carbonate, which is precipitate. So we kept the concentration of calcium low by precipitation. It precipitated as calcium carbonate. Or to form sorry, or to form volatile gases. If we say NH4X plus NaOH, so we have ammonium on the colloid, we're going to replace it with sodium using sodium hydroxide. So we have now NaX. Na took the place of ammonium in the colloid surface. And what was produced? The OH, NH4OH. NH4OH, this is very basic, and it will give you H2O plus NH3. NH3 is gas, and it can leave the system. So again, we did not keep ammonium in here so that it will push the reaction backward. So we took rid of this. In this case, we use something so that it precipitates. In this case, we use something that releases a gas. So we lose the ammonium in the form of NH3 gas. Okay, this is very important. Concentrate with me a little bit so that we understand this valence dilution effect. For exchange between cations of differing charge, diluting the solution favors retention of the more highly charged cation. This is the statement in general. This is the rule. We read it again. For example, if we take a cation that has 2 charges, divalent and monovalent, another one monovalent, for exchange between cations of differing charge, one divalent, one monovalent, if we dilute the solution, what happens? It favors retention of the more highly charged cation. That means the one with the higher charge, higher valence, will be the one retained or exchanged on the surfaces more than the lower valency. We'll take this example and see how it works. Calcium on the exchange complex, we added 2 ammonium to give NH4 2. Remember, 2 take the place of 1 for the 2 negative charges of the colloid. Then calcium is released in solution. The K for this reaction, okay, so we take calcium, the activity of calcium, or concentration. If we talk about concentration, we can take concentrations instead of activities. Okay, so concentration of calcium times the concentration of this colloid, the ammonium on the colloid, over CaX, and this is an ion, so you raise it to the 2, NH4 plus to the power 2 because of this stoichiometric. Brackets indicate concentrations in mole per liter. If we rearrange this same one by cross multiplication, you know, in Arabic you call it الضرب التبادلي, simple thing. Just if you look at this and how we ended having this, it's very simple by moving things using that cross multiplication rule. So now we are going to have the ratio of the ones on the exchange together and the ratio of the ones in solution separate. So NH4 2X, that's the exchangeable ammonium, over the exchangeable calcium equals K for equilibrium, the K of equilibrium, okay, times ammonium square, remember, because it has a square sign, over calcium. This is in solution. Remember, if you put X, these are exchangeable cations. The ones without X, these are the cations in solution. Because of the square term, watch that this has square and this one doesn't. We will see what does that mean. Because of the squared term on the right, the ratio of ammonium to calcium on the colloid surface changes with the total as well as relative salt concentration of the bulk solution. So what happens? What changes take place in the bulk solution? That means the solution, salt solution, away from the surface of the colloid. That's what we usually mean by bulk solution. Bulk solution, the salt solution, which is not affected by the surface of the colloid. It's the major part of the salt solution away from the colloid surface. So a solution having, let's take an example, ammonium and calcium equal concentrations in solution. A solution having ammonium concentration equals calcium concentration, each one of them equals 1 millimole per liter. So both of them have the same concentration. So if you take this, okay, NH4 square over Ca2, this ratio, NH4 square over Ca, it'll be, remember, the concentration of each one is 1 millimole per liter. So 1 square over 1 equals 1. So it's the same thing. So the ratio is 1. Okay, so that means this ratio now is 1. Now, upon tenfold, this is the whole purpose of this, the effect of dilution. We're going to see what does dilution do to the retention of the divalent against monovalent. So we diluted the situation and the solution 10 times. So instead of 1 millimole per liter, each one of them becomes 0.1 millimole per liter. 0.1. Remember, ammonium square, so we square 0.1 square over 0.1. So now it becomes 0.1 if you remove one of them with this one, so you end up with 0.1. Remember there, 1 to 1, 1 square over 1, 1. Here, 1.1 square over 0.1 equals 0.1. Remember, we diluted 10 times. Now the ratio is 0.1. So the ratio of ammonium to calcium is way down, way low. And that means, remember, it's equal to, this is constant. So this ratio, that means the ratio of ammonium to calcium was reduced, which means more calcium was on the absorption sites of the colloid. Remember, we calculate this because we know it to know the ratio on the exchange. We calculate this one by knowing the concentration in salt solution. So we have 0.1 square over 0.1, the ratio of the ammonium to calcium. So that means calcium is much higher here. So that's why it says back again, for exchange between cations of different charge, dilution of solution favors retention of the more highly charged cation, in this case, calcium instead of ammonium. Favors, it means it likes it, or it favors, it makes it better for it, for the divalent. Okay, the last thing we'll talk about, also another characteristic, exchange selectivity. Attraction of cations for negatively charged colloid surface is qualitatively described by electrostatic attraction and repulsion following Coulomb's law. Coulomb's law, remember, the attraction between positive, negative things, between positive charges, negative charges. A major limitation of this simple electrostatic approach is its failure to predict differences in preferences or selectivity of colloid surfaces for cations of the same valence. If it was just simple positive negative, then all cations, if they have the same valence, should be attracted by the same strength. But we will see this is not the case. So a major limitation, that means it does not explain everything. It has limited explanation of the simple electrostatic approach. Its failure, it fails, it does not give us the correct answer to predict the differences in preferences or selectivity of colloid surfaces for cations of the same valence. We'll talk about it in a minute to become clearer. Such preference is related to the relative hydrated sizes or to the relative energies of hydration of the various cations. So what are then, sorry, the reason for these differences that this simple Coulomb attraction, positive and negative, does not explain? Such preference is related to the relative hydrated sizes or to the relative energies of hydration of the various cations. So each one of these cations, even though they have the same charge, same monovalent, but their hydrated size in solution are not the same. We'll see what does that mean. Ions of smaller dehydrated radius have a greater density of charge per unit volume. Okay, to explain that, you know that all ions or atoms, we consider them as spheres. So if we have two ions without hydration, they're not in solution, that's their normal way. One of them is smaller than the other in their dehydrated condition. Ions of smaller dehydrated radius, which means the sphere is smaller, have a greater density of charge per unit volume. If one with small dehydrated radius and another with greater dehydrated radius, which means, remember, smaller radius, smaller sphere, larger radius, larger sphere. So that same charge has to be distributed over in one case, smaller surface, and the other one on a larger surface. So the density of charge will be different. If it's on the same smaller one, the density of charge on that surface will be higher than if it's the same charge distributed over a much larger surface. Hence, what is the result of that? They attract waters of hydration more strongly and have a larger hydrated radius. So the one with the smaller dehydrated radius have higher density of charge on their surface, they attract more water. Remember, water molecules are polar, so they get attracted more to these smaller dehydrated, and they become, their hydration size is larger. So they have larger hydrated radius. An ion of larger hydrated radius is held less tightly by column attraction. Of course, if the ion, when it is hydrated, and that's where the exchange takes place in an aqueous system. So they are hydrated. So that means if it is hydrated and it has large hydrated size, large radius, large surface, remember the same, that charge has to be distributed over larger surface, so its attraction to the surface of God will be weaker. So it will be held less tightly by the column attractions. The most important factor determining the relative extent of absorption or desorption of a given ion is its valence. So if we are going to decide which of the cations are attracted stronger to the colloid surfaces which are negatively charged, of course we know. So first, the most important thing is the valence. The most important factor determining the absorption of it is its valence. So you cannot compare monovalent with divalent. Automatically, divalent will be attracted more. Trivalent will be attracted more than both of them. Divalent ions in general are retained more strongly than monovalent, and trivalent ions are retained even more strongly. What I have just said. Within a given valence series, the degree of replaceability of an ion decreases as its dehydrated radius increases. Remember, we already talked about the dehydrated radius. That means if it has smaller dehydrated radius, remember, higher density, it will have larger hydrated radius because it attracts more water molecules, and so its attraction will be less. So the degree of replaceability of ion decreases as its dehydrated radius increases. Remember the replaceability, how strong another cation will replace it. That's not its replacing power, the replaceability, that means another cation will take its place. That means it's easily displaced or strongly displaced. So its replaceability, that means another ion taking its place, decreases if its dehydrated increases, because that means it's taking, remember, when its dehydrated increases, that means it takes less water around it. That means it will be smaller in the hydration form. It will have higher density of charge on it. Then it will become harder to be replaced. It will be held stronger. Think about it. It's very simple. Just read again and think about them and keep thinking about these. I am sure you will understand them easily, but just simple, and read them over and over so that you understand exactly what we're talking about. Okay, we talk very quickly about, I'm not going to go into detail. I used to teach the exchange equations a lot more, but this time I'm gonna just introduce them very briefly. To predict the effects of irrigation, weathering, fertilization, and acid rain on soils, it's necessary to predict the exchangeable cation composition in equilibrium with this input. So this is important to predict, so we can expect the effects of irrigation, weathering, fertilization, acid rain on soils. It's necessary to predict the exchangeable cation composition in equilibrium with this input. We have to know what's going on. What are the exchangeable cations that are? Exchangeable cation chemistry can also provide valuable clues about plant elemental deficiencies or imbalances, rates of toxic metal movement, and tendencies toward soil dispersion. All of these things we can learn from what are the cations that are absorbed on the colloid surfaces. Several equations describe cation exchange process. Each has its own set of characteristic and merit. Characteristics, how we characterize its properties, and merit, it's how good it is. Its merit, is it benefit, good, bad, what, better than others? That's what the merit is. The choice of a particular equation often seems to be subjective, which means so many scientists put so many equations, so it's up to that individual scientist that put out and believed in that type of equation. So it's subjective. That means we do not have really rigid scientific rules to say this is better than this. It's all subjective. That's why we have so many of them, which I will not cover, like I said, because I don't think it's that important at your level. But let's take a quick look at the most general type of cation exchange relationship is what we call mass action equation, which you have studied in chemistry. Okay, so we have CaX2, remember, same, we have covered all that, X2, that means this one has only one charge, so we needed two of those X for one calcium, plus two sodium, so you have two of those colloids, each one of them carrying one sodium, calcium is released, resulting in the reaction coefficient, or K of equilibrium, NaX square times the activity of calcium over the activity of CaX plus times, the Na plus. Okay, X denotes the exchangeable form of the cation, and parentheses denote activities of soluble or exchangeable cations. If it is with X, exchangeable. If it is without, that means it's the ion. The major problem in all exchange reaction is evaluating the activity of the exchangeable cations, since their activities cannot be measured or calculated precisely. That's why I decided not to go through this and bother you with so much, because so many scientists think of how hard it is to find out what's the activity. How do we calculate activity of something that's adsorbed, exchangeable on the surface of colloid? Of course, the one in solution we learned how, using, remember, d by Huckel equation, we can do from the concentration and then calculating the single ion activity, gamma, if you remember, and then you find out the activity. Okay, you multiply the concentrations times gamma. If you remember all that, we can calculate this activity in solution. But the one on exchange, it's not easy. We cannot do that. So we have limitations. That means it's not really, it has very hard limitations. Cation and anion exchange are considered separately, acknowledging their simultaneous presence is rare. So although we always talk about mostly cation exchange, and that's what's important in our soils in Jordan and most of the arid areas, but also there are areas in the world where they have anion exchange, and we already talked about that also earlier. The cation or anion exchanger, the complex is assumed to possess constant exchange capacity. Often, however, the capacity varies with the exchangeable ion, with salt concentration, and with pH. So the CEC, the amount of charges on it, not always constant. It can change, and we studied how it affected, remember, the pH-dependent charges already we covered. Stoichiometric one-to-one ion exchange is generally assumed. That means 1-for-1. Apparent exceptions are usually explained by simultaneous absorption of molecules or by complex ion formation. So sometimes this is not the case. One ion for an ion, one molecule for one molecule. We have some cases that doesn't apply. I mean, just for you to know, these are limitations. You don't have to understand completely. This is a little bit advanced for you to, we don't go through this. Complete reversibility is usually assumed. We always assume complete reversibility, and usually it's not true. The last thing I will go through is how do we measure the cation exchange capacity? Remember, we talked about it a lot, but how do we do it in the laboratory? I will try to explain the methodology that's used. Several methods are available to determine the CEC of a soil. All methods rely on the ability of an index cation to replace the native readily exchangeable ions. Remember, we know that any soil has normally more than one type of native exchangeable ion. It has several, depending on whether it's Mediterranean area, it's a dry area, it's heavily in the wet areas. It depends on where is the place of that soil. The type of the ions that are there is different from one soil to another. But we know that there is not only one ion, one type of cation on the surface of the soils. So this is variable. To replace, that means to choose one, what we call an index cation. One index, we know what it is. We choose one cation. We want that cation to replace everything that's on the colloids surfaces. So we call it index cation because we know, we choose it and we know where it is. Two general categories of CEC methodologies are employed. So there are two general types. The first involves the displacement of native cations and the saturation of the exchange complex with an index cation such as sodium. So the first one, that's what we said about the index. I choose sodium and I want sodium to replace, to displace, to exchange all the cations that are on the exchangeable sites of that soil. So we choose one, so like sodium, saturate, that means all the sites, all the exchangeable sites on that colloids, the colloids of that soil will be occupied by sodium. So we saturated the soil surface with this ion. The adsorbed sodium is then displaced by a second index cation, such as ammonium. We choose another one and we replace the one that was adsorbed. So now we saturated the soil with sodium. We know that we have only sodium. We bring another cation like ammonium and let it displace the sodium from the surface. And this is also another index because we choose it. The moles of sodium displaced by ammonium, okay, remember sodium saturated all the surfaces, nothing there except sodium. Now we get it out by replacing it with ammonium. This sodium, what they displaced, are equivalent to the moles of exchangeable surface charge per mass of soil. That is the one when we measure, it determines how much negative charges on that soil, how much cations it can absorb from this. We will see, and we will see the calculations in a minute. The second technique involves the displacement of native readily exchangeable cations by an index cation that is normally not native, such as ammonium. So this is a different technique. We displace all the native, just like we did the other one, but we choose one ion which is not common in that soil or rare. It doesn't hardly exist in that soil, especially say like ammonium. Then subsequent determination of the displaced calcium, magnesium, potassium, sodium, and aluminum and magnesium, if the soil is acidic. If it's not acidic, then we determine these mostly. In the solution, we displaced. So we take ammonium, we let it displace all the cations from the soil colloids. Then we collect them. Then we determine each one of them, and we add them together. That will give you the what we call CEC. A summation of the moles of displaced charge is then a measure of the effective, we call it, in this case, effective CEC. That's why we put the E in front of it, effective cation exchange capacity. This second method also allows for the determination of the exchangeable base cations present in the exchange complex, sum of centimole of charge of calcium, magnesium, potassium, and sodium adsorbed. So there is a characteristic called the exchangeable base. So we can determine that if we use this method because we calculated each one of them individually. The other one we will see when we do it in a minute, we measure only sodium that took the place of everything. Here, we remove everything and we determine each one individually, then we add them together. Now there are two ammonium acetate solutions that are used, pH 7 or 8.2. The ammonium acetate method employs two index ions, sodium and ammonium. In pH buffered acetate solution, we buffer it so that the pH doesn't change. to determine the potential CEC of the soil. The measured CEC can either over or underestimate the field actual CEC of a soil depending on the field pH of the soil. Remember, that's why we have choices. What is the characteristics? What is the pH of the soil we are going to measure its cation exchange capacity? Based on that, we choose which solution. We choose the one buffered at 7 or the one buffered at 8.2. So if the field pH, remember, field pH, that is the pH of the real soil in the field, is greater than the buffer, say if we chose 7, and the soil has a pH of 8, so if the field pH is greater than the buffer pH, the ammonium acetate will underestimate CSC. That means if the soil has a pH of 8 and we used pH 7 buffer, that means this determination will give us a value which is lower than the real value. Underestimated will give us a lower value of the real CC. Why? Because we know they are pH dependent charges. So if the pH of the soil is 8, at 8 it will have higher negative charges than pH 7. If we buffered it, we did not allow it to be like the real situation in the field, we will not have the same number of negative charges. We will have lower negative charges, which means lower CEC. So that's why this type of buffer will underestimate. Of course, the opposite. The buffer pH is selected with knowledge of the soil pH. So the first thing we measure always the soil pH, then we decide which buffering system we're going to use to determine the CEC. For the CEC of acid soils, pH 7 buffer is used, while the CEC of alkaline soils, which is our case, is determined at pH 8.2 in an effort to minimize calcite, calcium carbonate dissolution, and again, not to underestimate or overestimate the cation exchange capacity of the soil. So we will concentrate, we are going to use the pH 8.2 ammonium acetate, sodium acetate, ammonium acetate method was developed primarily for application to alkaline soils, like in our cases. Soil is initially centrifuge washed a number of times with a pH 8.2, 1 molar, remember, high concentration. Remember, we said to exchange something, we need to use high concentration to make sure that we are replacing all the cations that are on the colloids. Okay, so soil is initially centrifuge washed a number of times with a pH 8.2, 1 molar sodium acetate solution. So we bring the solution. We have a certain amount of soil, a known, we'll go through the calculation in a minute. We have a known mass of the soil. Okay, we have a known mass of the soil. We add solution of 8 buffered at 8.2, pH 8.2 of the sodium acetate, and we shake it with the soil, and then we centrifuge. Then we throw it away. We do it several times. Why? To make sure remember we use the term to saturate the soil with sodium, to make sure that sodium replaces all the cations that are on the exchangeable sites of that soil. The successive washings remove soluble salts and saturate the exchange complex with the sodium index ion. Then the next step, the soil is then centrifuge washed with 95% ethanol solution to remove occluded sodium. What do we mean by occluded? Now we have sodium on the exchangeable site. This is attracted to the surface. It's not removed. But we have also in the soil pores, we have that sodium acetate solution. That's extra. We don't want it. It's not exchangeable. But we remove it with something that does not affect the sodium on the exchangeable site. So we remove with ethanol, with alcohol. So we use it several times again. We remove all the occluded, the excess sodium that's not on the exchangeable site, that's on the soil surfaces. We remove it because that will give us errors. Soil is then repeatedly washed with a pH 7.1 molar ammonium acetate solution to displace sodium for analysis. Remember, now we have a soil saturated with sodium. Only sodium is there and no sodium anywhere else except on the exchangeable side. Now, how do we measure the CEC? We want to remove the sodium and measure it. How do we remove it? We remove it with ammonium acetate. The ammonium will be strong to replace the sodium and get it out. This time, every time we repeat the process, we collect the sodium. We don't throw it away because we are going to determine how much sodium we have. That will be representing the CEC of the soil. So repeatedly washed with pH 7 1 molar solution to displace sodium for analysis. We collect it for analysis. The centimole of charge of displaced sodium divided by the sample mass in kilogram is the CEC. We'll see, we'll take an example and go through the calculation. So again, remember, if you understand the principle, if you are ever given in an exam, I will never give you the same numbers here, but the principle is the same. If you learn how you do it, it doesn't matter anything that can change. Well, you should be able to calculate your CEC. So we'll take this example as an example. 2 grams of soil treated with pH 8.2 molar sodium acetate solution. Remember, so many times, and we throw it away because we want the sodium only to saturate this time, and then followed by removal of entrained, the same as occluded. How do we do it? With ethanol, remember, step entrained or occluded sodium, we remove it by alcohol. Then the sodium saturated soil is then treated by subsequent following each other, several, one after the other, washing with a pH 7 1 molar ammonium acetate solution to remove the sodium. The supernatant solutions from the ammonium acetate washings are collected. We collect because we want that sodium. We want to measure it, see how much it is, collected and combined in a 50 milliliter volumetric flask, which is brought to volume with distilled water. So that we calculate concentration, you have to bring it because these washings might not come exactly to the volume we want. So you bring it to volume with little water to the line of the volumetric flask. So now we know we have 50 ml volumetric flask that contains all the sodium that was saturating that soil complex. The solution is analyzed by atomic emission spectrometry for sodium. So we analyze and see how much sodium we have. I know this is a little longer lecture, but this is the last slide, how we go through the calculations. Concentrate. So if the total sodium concentrate, we took this sodium to the lab, we determine it by flame photometry, by atomic absorption, whatever type, there are so many different ways. And we find the concentration, remember, in that 50 ml volumetric flask, concentration of sodium, 119.4 milligram per liter. Remember, milligram per liter is the same as parts per million. We learned that, but this is the official, this is the better way, scientific way, milligram per liter, or microgram, remember, per milliliter, same, milligram per liter, microgram per milliliter. So if 119.4 milligram per liter. Liter is 1,000 ml, but I don't have 1,000. We have only 50 ml. So the 50 ml, how much it contains? 119.4 milligram. This is in 1,000 milliliter. So how much I have in the 50 ml liter? Then we get 5.970 milligram of sodium. Okay, I want to change it to millimole. The milligram, remember the atomic weight of sodium is 23. So we divide the milligram by the atomic weight to give us millimole. So it gave us 0.260 millimole, the total amount that came from this volume, that total amount that came from our soil, that came from the 2 grams of soil. 0.26, remember, the correct units, always, CC, you have to put the correct units, which are centimole of charge per kilogram of soil. That's the only acceptable unit for cation exchange capacity. So we want to change it to that, 0.260 millimole. And we know that the centimole is 10 millimoles. So we divide by 10 to give us 0.0260 centimole. Centimole is larger than millimole. Remember, centi 1/100. milli 1/1000. So we change it to, by dividing over 10, divided, we change it to centimole. So now we have the correct unit here, centimole of charge coming from sodium. But the mass, we started with 2 grams, the correct unit we want per kilogram of salt. So we say that this came from 2 grams of salt we started with, 0.0260 centimole of charge per 2 grams. Then how much 1,000 gram, which is the kilogram, will have, we multiply by 1,000. This, when you divide this, will give you per gram. This, when you multiply by 1,000, will give you 1,000 gram. So 13.00 centimole of charge per gram. This is the CAC of the soil, and this is the correct unit. This way, we end up the lecture, and I hope it was not too much for you. Read it again. If you have any problem, contact me, and I will try to help you in any way I can.